Hello, students. I hope you're all doing very well. And let's make the best out of the current situation that we are all in. And though, as a teacher, I would obviously like to teach differently by a different mode. And we're all used to board and a chalk, especially for a subject like discrete mathematics. But I've tried to, make the notes so that you can understand it well. And obviously, you can use other material that are available on the internet. And you've got a lot of resources which are available on the internet. And then can understand this topic. The purpose of creating this small video, this is to accompany the PDF of notes that I'm sending, because sometimes it can be a little difficult to understand just the notes. And so I would assume that you have gone through the notes at least once and have understood it, because obviously a video cannot be as long as a class lecture we have in class. Okay, so the first one that I sent, this is corresponding to that first set of notes. So this is chapter 9, which is linear recurrence relations and recursive algorithms. And you just go from the book itself, read the first section, which is on introduction, which they have talked about different relations or different situations that we see in our daily life, how we can state a different problem. And what they're essentially trying to tell in that section 9.1 is that how we can present or specify one term in terms of its previous terms in a series. Like, you know that a numeric function is basically a series of numbers, right? So when you can represent that same numeric function in a fashion, in a recursive way, then you have a recurrence relation. And I believe that in first semester as well, you would have done some recurrence relations. Two classic examples of recurrence relations that we talk about are the Fibonacci series, in which one term is the sum of the previous two terms, and another is the factorial. Okay, so then coming to section 9.2, this is recurrence relation. And again, just taking a simple example in which you have a series, a numeric function, and the series is 3 to the power 0, 3 to the power of 1, 3 to the power of 2, and so on. And you have 3 to the power of r. And if you generalize, this is the numeric function in terms of writing in terms. If you recall, in the previous chapter, we had written the numeric functions in two ways. Either we were listing it as what the terms are, and writing them as in between circular brackets, all the terms one after the other, comma separated, or we used to write a numeric function in the form of a generalized expression. So for this particular numeric function, you would have AR is equal to 3 to the power of R for all R greater than equal to 0. Now, you know that what are numeric functions? As I just mentioned, they're just a sequence of real numbers. And we had also seen in the previous chapter that every numeric function can be represented as a generating function and vice versa. So the generating function corresponding to AR is AZ equal to 1 by 1 minus 3Z. And sometimes, as we have been discussing earlier also in discrete mathematics, sometimes it is you just try to represent a particular problem in a different way, so that sometimes it is easier to solve that particular problem. So that is in the same way, when we are talking about recurrence relations, there may be certain numeric functions which are a recurrence series, like a Fibonacci series, or you have a factorial of a number and all. So, okay, to find another alternative representation from the above, we can see that the value of AR is 3 times the value of AR minus 1 for all R. That means every term is 3 times the value of the previous term, and that's how we have a recurrence relation. AR is equal to 3 AR minus 1. Now, in this case, obviously you need to know the first term, only then you can further generate the other terms. Like here the first term is 3 to the power of 0, so unless you know what the first term is, you will not be able to generate the second and hence the third and so on. Okay, so the expression along with a0 specifies your numeric function a, which we have been talking about. Another which we are talking about is your Fibonacci series of numbers. Now, you know that as we were just discussing, a Fibonacci series at every term is a sum of the previous two terms. And here again, we know what are the two starting terms in a Fibonacci series. The two starting terms are 1 and 1. Okay, now again, representing the rth number, you can see this particular equation, and then you can also see what is the corresponding generating function. Now, as you can see, as compared to the previous example, it's not very easy to understand the numeric function, or even how from the numeric function you have got the generating function. So this is an example where finding a recurrence relation of the corresponding numeric function will help you further understand like how to solve a particular problem. Okay, so an easier way to represent the sequence is to represent it in a recursive relation. So you have AR is equal to AR minus 1 plus AR minus 2, and obviously with the two initial terms, which is A0 equal to 1 and A1 equal to 1. So this is a recurrence relation corresponding to the Fibonacci series. Okay, so if we generalize, we can say that for a numeric function a0, a1, a2, and so on, ar, an equation relating ar from any for any r to one or more of ai's, where I is equal to r, is called a recurrence relation, or it's a difference equation. Now you would see, as we proceed in this particular chapter, there are certain, we would be talking about or referring to the difference equation, and that I think, if you recall, you have done in class 11 or 12. Okay, and as we will go in the subsequent sections, you'll see, and you'll remember how you have done it, what you have done. Okay, so it is sometimes easier to obtain a recurrence relation representation of a numeric function along with the set of boundary conditions. So in this case, as in the case of Fibonacci series, we can obviously see, as here, that the recurrence relation representation of your numeric function is much easy to understand and to relate to as compared to the numeric function, or the rth term of the numeric function, or to your generating function. Okay, and the given values of the function, in this case a0 equal to 1 and a1 equal to 1, in this case of the Fibonacci series, are called the boundary conditions. So corresponding to a numeric the corresponding numeric function is referred to as a solution of the recurrence relation. Okay, so as we will be seeing further in the subsequent sections, the objective would be to find the solution of the recurrence relation. So again, what will you need? You will need a recurrence relation, and you would need the boundary conditions, and then you would like to find a solution. So ultimately, what the solution would be, it would be a you would come to finding what the numeric function is. Okay, now coming to the next section, which is linear recurrence relation with constant coefficients. They are also called the kth order linear recurrence relation, or the recurrence relation of degree k. Now you need to remember that here we are talking about a subset of your recurrence relation, and that's why we are calling it linear recurrence relation with constant coefficients. Okay, now coming to the fact of kth order. Now we have seen, for example, Fibonacci series. In this case, you have like three terms, and you need to the third term is based on the previous two terms. So if I have a recurrence relation of the form C0AR plus C1AR minus 1 plus so on CKAR minus K equal to FR. So here all the C's are your constants, and this is called a linear recurrence relation with constant coefficients. Now you have to, even if your equation is given in a different way, how do you identify that it is a linear recurrence relation of constant coefficient? We'll just see subsequently in certain examples. Okay, so you bring all the AR terms on one side, and then you will also get to know what the FR is. And when we are trying to find the solution, the FR part is also very important. Okay, now to actually know whether it's a linear recurrence relation, rather whether it is, which is the order of the recurrence relation, the C0 and the CK have to be non-zero. So these two constants have to be non-zero. So that means, as you can see here, you have AR term is necessary and AR minus K term is necessary. Now for the AR term and the AR minus AR minus K term to be present in your particular equation, the constants corresponding to these terms, that is C0 and CK, they have to be non-zero. So that is what is written here, that provided that C0 and CK are non-zero, that is AR is expressed in terms of previous K terms. Okay, so if you can see here, if I try to rearrange this equation in, I'll get AR equal to FR minus all the other terms divided by C0. Okay, so there will be K terms based on which I can find my the AR term. Okay, now we are now seeing certain examples of recurrence relations, and we are trying to find whether they are linear recurrence relation, and also the, if they are a linear recurrence relation, what is the degree of that recurrence relation. Okay, now in the first example, AR is equal to 2 an is equal to 2an minus 5. Okay, so you, as you can see in the generalized equation, you have all the terms, so it is not necessary that all the terms in between have to be there, but the an term and in the an minus k term have to be there. So if I see from here, what is the value, if I rearrange, what equation will I get? If I want to bring it of the form in which on the right hand side I have to have an FR, I can rearrange of this first example, an minus 2an minus 5 is equal to 0. Then our FR will become 0. Okay, so in this case we know that the nth term and n minus kth term, the constants are non-zero. It is a linear recurrence relation, and it is of degree 5. Why? Because you have a n minus 5 term. So the k is 5. That means it's a fifth degree linear recurrence relation. Now coming to the next example 2. An is equal to an minus 1. Now, this is not a linear recurrence relation, as n is not a constant. Remember, all the coefficients of AR minus 1 and so on, it has to be a constant, and you know that n is not a constant. Hence, the equation in number 2 is not a linear recurrence relation. Okay, now let's see the third example. Okay, now this third example, again this equation is not a linear recurrence relation. Why? Because it is not linear. It is a recurrence relation, but it is not linear, because the term an minus 2 is of power of 2. Okay, so all an or an minus 1, all these terms have to be a power of 1. That's why it is a linear equation. Okay, so that's why the third example is not a linear equation, linear recurrence relation. Now see the fourth one. So an is equal to an minus 1 into an minus 2. Now in this case, remember the an terms, they have to be terms have to be added, or why we say added, because if c k value or c I value is negative value, then you can say they are subtracted, but you cannot have an terms being multiplied. Okay, so this is not a linear recurrence relation. Okay, as an minus 1 and an minus 2 are factors of a term. Now, so remember, like if you see even your factorial is a recurrence relation, but we will not call it a linear recurrence relation. Okay, so in this chapter, the example we have taken is of a Fibonacci series, which is a linear recurrence relation with constant coefficients. Okay, now coming up to the fifth example, 2ar plus 3ar minus 1 is equal to 2 to the power of r. As you can see here, you have r minus this term is r minus 1, so that means it's a first order linear recurrence relation, and here in this case your fr is 2 to the power of r. Okay, the next is the next two equations. If you see, you can just look at them again without seeing my answer, the answer that I've written on the side. In equation number 6, you can see that you have a AR term and then you have a AR minus 2 term. So here the value of K is 2. So this means it's a linear recurrence relation of the second order. Even in the 7th equation I have here, AR, you have a AR term and you have a AR minus 2 term. So in this case, again, it is a linear recurrence relation of second order. Okay. Now take another example. 3AR minus 5AR minus 1 plus 2AR minus 2 is equal to R square plus 5. So obviously you have a AR term and you have a AR minus 2 term. So what do you have here? You have a linear recurrence relation of order 2. Okay. Now suppose two values, you're not talking about A0 or A1, you have two values A3 and A4. These values are given to you. So as you can see, these are consecutive values. Okay, and you have to find, say, A5. Now that means to find A5, that means your R is equal to 5. What I have done is I have also written that equation, the linear recurrence relation, in a form in which I have a AR term. So your AR is equal to 1 by third of, and then whatever is written here, you can see. So you can find the value of A5 and then you can find the value of A6, and you can even go back and try to find the value of A2, and then you can actually find the value of A1 and A0 and so on. Okay, so what have we seen here? That with any two consecutive values, say in this case we took A3 and A4, we are able to get the complete all the terms of my particular sequence. I can even get the previous ones, that means A0, A1, A2, and also the ones beyond it, the given terms. I can also find A5, A6 and subsequently. Okay, so in general, for a kth order linear recurrence relation with constant coefficients, if k consecutive values of the numeric function are given, are known for some m, that means for the kth order and the mth order, for some r, the value of am can be calculated accordingly. Okay, so as we will see subsequently, first of all you want to find a solution, that means you want to find a numeric function corresponding to a recurrence relation. Here we are talking about just linear recurrence relation with constant coefficients, so that reduces the kind of recurrence relations we are talking about. Next, if I have to uniquely get a solution or find a numeric function which is my solution for a recurrence relation, linear recurrence relation of constant coefficient, if it is a kth order, then I need a recurrence relation, then I need k consecutive terms. And in the subsequent examples, if I have less than k terms or if I have more than k terms, either I will not be able to find a solution, or if I am able to, it will not be unique. Okay, so to uniquely identify, you will need k consecutive terms. Okay, so let's see the other examples. So for a kth order linear recurrence relation with constant coefficients, fewer than k values of the numeric function will not be sufficient to determine the numeric function uniquely. Okay, so here we're taking an example, and as you can see in this, I've named this as equation number 1. So in this equation, as you can see, you have a AR term and you have a AR minus 2 term. Okay, so you know it is a second order linear recurrence relation. The previous example also, which we had just taken, is also a second order, and we were given two consecutive terms and we were able to uniquely find a solution. Now in this case, you're only given A0 is equal to 0. Now, you know, as I've just stated, that it's a second order linear recurrence relation with constant coefficients. So, the given boundary conditions, with just one boundary condition instead of two, you can have many numeric functions which satisfy this particular recurrence relation. So, what we have seen here is that even though you're able to find a solution, that means even if you're able to find numeric functions which satisfy the recurrence relation given that single boundary condition of a0 equal to 2, but there are multiple solutions, there is no unique solution. Okay, so thus with only one boundary condition, the second order linear recurrence relation, we cannot uniquely obtain its numeric function. Also, more another thing is that also if we have more than k values of the numeric function, they might make it impossible for the existing servo numeric function that satisfies the recurrence relation and the given boundary conditions. So that means, for example, if you have and the example is given below. So if you have particular for that same equation that we had up here, so as you can see, it's a second order linear recurrence relation, and you're given three boundary conditions. A0 is 2, A1 is 2, and A2 is minus 2. Now, even though you put these particular values, you will see that these values do not satisfy your recurrence relation, and hence you will not be able to find your solution. Okay, so that if your linear recurrence relations, if it has less number of boundary conditions than k, then you will not get a unique solution. If more boundary conditions are given than k, then you may have a situation in which there is no solution that you get because they don't satisfy all the boundary conditions as well as your recurrence relation. Okay, so also if kth order linear recurrence relation is not a linear relation with constant coefficients, k consecutive values of the numeric function might not unique satisfy a unique solution. Okay, so in this case again, so first of all, we don't even attempt to try to find the solution of a non-linear recurrence relation, but here as we can see, it is not a linear recurrence relation, and hence you cannot even get a unique solution even if if this is a recurrence relation of order 1. You're given one boundary condition, a0 is equal to 1, so that part is satisfied, that the kth order and then there is 1, the order is 1, and you're given one boundary condition. But in this case, the given recurrence relation is not linear, and hence again you will not be able to find a unique solution. Okay, so these are just different properties. So you sometimes, though it's a very trivial question, but in the exam, maybe in a 1 marker or 2 marker, the first part, you can get whether given the linear recurrence relation, is it linear or not, or what is the order of the linear recurrence relations, or can you find a solution. So first thing is that if it is not linear, unless you know whether it is linear or not, whether that many number of boundary conditions, k boundary conditions, are given or not, you will then right in the beginning be able to identify that you're not will not be able to get a unique solution, or no solution is possible, and hence you will not try further to find the solution. Okay, so this basically ends the part 1 of chapter 9, and in the next part we will start to find what is the solution of the linear recurrence relation of constant coefficients. Now, finding that solution also, it is in parts, so we will have a total solution, which is the sum of your homogeneous as well as your partial solution. The part 2, which is how to find the homogeneous solution, I've also shared with you. So there will be a video accompanying that, and then subsequent videos accompanying the notes corresponding to the different parts of the chapter. So I repeat again, read the chapter again, and then go through the video also, and then I believe then you'll be able to understand it well. Otherwise, then you can call me, or I can solve your queries on personal chat WhatsApp. Okay, thank you. Good day.